Okay, welcome. And I'm Carlo and I will be talking about the brain morphometry using diffusion MRI. I'm not aware that we had in this summer course anything about brain morphometry. But if you think the way typically we analyze imaging data, right, beyond what a radiologist could do, we have different brains with different shape of the brain. And if we want to do any voxel-wise assessment of what's going on in the brain, we need to morph the brains from their original shape into a target template, okay? So essentially, these are before were the three subjects just superimposed, and then you can see as they get morphed into a common space, they appear much sharper, okay? And we do it, we need to do it so one way or another for any voxel-wise analysis we do. These are not new concepts, obviously. So here is from a book that is about 20 years old, from Ashburn and Freeston, voxel-based morphometry. And they were already pointing out that we can look at differences in brain shape. So our question, biological question, can be related to differences in brain shape or to differences in local composition of brain tissue. And then we can essentially take two different approaches that are not opposite to each other. They could be complementary. So we need to morph the brains into a common space to do any voxel-wise analysis. And then the only thing we could care about is just the voxel-wise values at each voxel location. Or we can actually look at the deformation fields. So what type of deformation did we have to apply to each individual brain to bring them into a common space, okay? And this is also, these are all things that have been around for a while. And one metric that is very important to look at essentially the deformation field is the local change in volume. Okay, and this local change in volume is related to this complicated term, the Jacobian of the transformation. So you take one brain, you transform this brain into a template, and then at each voxel, you can assess what is the difference in volume. So for instance, if we go from, we have this brain, and this is clearly a pathological brain, has a very thin corpus callosum. This is essentially a template brain of normal subjects. And so we can morph this brain into the control template. And then this is essentially the same brain of the patient once has been morphed into the template as best as we can. And then we can compute this is actually the logarithm or the determinant of the Jacobian of transformation. This image, let's spend a few seconds on understanding this image. So this image will record through the course of all this talk. So where you see the background here is 0. So essentially they will be consistent with no changes in volume to morph the brain into the template. When you see dark, it means that we have a negative value of the logarithm determinant of the Jacobian. So it means that in the patients, we have a smaller structure than in the controls. And in fact, we see here that the corpus callosum was very thin. To morph it into a normal corpus callosum, we have a negative determinant of the Jacobian, right? So when you see dark, it means that the patients have locally a smaller structure than the controls, than the target, okay? And vice versa, when you see bright, like here in the ventricles, it means that the patients had a larger structure than the controls, Okay, this is the way of looking at these images. And there has been a number of applications of this so-called tensor-based morphometry using T1 weighted images. Why T1 weighted images? Because they are high quality, they are undistorted, they are morphologically faithful. And so there has been, decades of publications about that. There has essentially been nothing using diffusion MRI data, okay? And again, we didn't have this year any introduction to diffusion MRI. I think that the organizers of the talk, encourage people to go and study the previous courses and so on. But as you probably know, diffusion MRI provides additional information, in particular in white matter. So we are able to identify, based on their orientation, based on their anisotropy, within a region that would appear homogeneous in T1 weighted images, we can identify individual bundles of white matter. So we say that since diffusion MRI contains this additional information, we may actually look at registration that is driven by diffusion MRI information, and that could be a more accurate and more informative registration. So this was our hypothesis a few years ago. There has been some example of tensor-based morphometry done with the diffusion-related matrix, but not really with the whole tensor. So there has been a registration based only on fractional anisotropy images, registration based on the tensor deviatoric. Actually, this was an excellent software. DTITK is called, and there is essentially one paper suggesting registration using the whole tensor, okay? I want to point out actually this other approach. This is a more sophisticated approach. It uses the data that, a larger set of data that is necessary to compute the diffusion tensor. And it has also a lot of implication in terms of the analysis of the data. So it's a more sophisticated approach that, if you are interested in looking into, could be worthwhile exploring. Just to prove that, again, it seems quite trivial. They say, why nobody has done morphometry driven by diffusion data? But, if you do not believe me, if we go to the authority on scientific knowledge, Wikipedia, and you look at under brain morphometry, you see that diffusion-weighted MR brain morphometry is still an empty field. So it's sort of still a virgin territory that we could invest on and do some original research on. So essentially, the goal was to achieve a robust and accurate diffusion MRI-based registration that could be used to perform TBM DTI. So maybe one reason why there has not been tensor-based diffusion tensor-based morphometry is that, unfortunately, diffusion-weighted images suffer from significant image distortion. Okay, so it's like in fMRI. Okay, these images are acquired with echoplanar imaging, and so depending on the phase encode direction, you typically have distortion in the phase encode direction. So here, if the phase encode direction is right-left, you can see that signal is piled up on this side and expanded on this side. If you invert the sign of the phase encoding blips, you will have exactly the opposite. And typically, what is done that is less disturbing to the eye, but is still a significant distortion being present, if you acquire with a phase encoding direction anterior-posterior, you have this type of distortion. But you can see that they are less disturbing to the eye because they respect the symmetry of the brain, but still you have, look at the temporal lobe, the signal can be piled up down here with the negative blips and piled up there with positive blip. So how can you do reliable morphometry if you start with images that do not faithfully represent the morphology of the brain, right? So first thing we need to do is to solve that, okay? And O'Connell-Fanoglu in particular, this actually is more on the correction, is to show that even in conventional, even if you do not do morphometry, the community for a long time has sort of ignored these distortions in the diffusion-weighted images, because they say, okay, they affect all the DWIs the same way, so essentially we compute our tensor fine on a voxel-wise basis. But if you look at the results that you can have just for doing tractography, this is actually quite compelling. So here is essentially a sagittal reconstruction of a diffusion tensor field on distorted images. And if you follow the direction of highest diffusivity from which you can do tractography, you can see that if you start here, you tend to go toward the back of the brainstem when you are down there, okay? So in this, you are not really following the corticospinal tract faithfully. Now, believe me, it doesn't seem so, but here nothing has changed with the actual diffusion tensor information. The only thing that this is the same image here, but corrected, in which the morphological distortion was corrected. And now, if you follow the tensor information, this eigenvector information, you actually follow the pathway properly, okay? So essentially, if you are even, the take-home message is, even if you are not interested in diffusion tensor-based morphometry, but you are just interested in tractography, care about correcting the distortion in the echoplanar images that you used to compute your tensor. And this is another example of the consequences of not correcting it. So if you have distorted images, this is essentially probabilistic tractography in a population of subjects, seeding at the level of the brainstem and seeing where the tracks go. And as you can see here, so essentially the color is associated with the probability of having a connection, right? And you can see that the probability of connection is sparse and is also kind of diffuse and so on. This is the same data after morphological correction of the DWIs. And you see that this is clearly not a feature of the anatomy or differences across subjects. This is really something that was an artifact of the data being distorted, okay? So it's important even for tractography in particular to correct the EPI distortion. So this is one of the approaches that O'Connell-Fanoglu in our group has worked on to correct. I think there are other approaches out there. Top-up, for instance, is very popular in FSL. And the most efficacious approaches used so-called blip-up, blip-down data. So data acquired with opposite phase encoding direction. So two sets of data with the blip-up distortion in one direction and distortion in the opposite direction, okay? When you finally correct the morphology of your individual data set, then the next step is to have a way of going into a common space. Okay, and this is again work from by Okan in our group, and this is called Dr. Thomas. So we have papers with all these doctors, Dr. Buddy, Dr. Thomas. Doctor stands for diffeomorphic registration, which is a complicated term, but essentially the most important aspect of diffeomorphism is that you assume that you have a one-to-one correspondence between a source and target, okay? And then we can discuss about that. But this is essentially the next step. So when you have computed your tensor with corrected images, you can register your images into a common space. I will not go through the details of what Dr. Thomas has, but one important aspect that it has is that it uses all the features of the diffusion tensor to achieve a good registration alignment of white matter, gray matter structure in CSF. So you don't want only to register well white matter. You want to register well all brain structures. And then these are other features, larger deformation capability, tensor reorientation during optimization, and can be applied to other images, and so on. Atlas creation strategies, and then also it can deal with the pathology, regions that essentially do not actually satisfy this diffeomorphism condition. So I hope you do not suffer from light-induced epilepsy, because it is kind of flashing. But anyway, we are going through here a movie of I don't remember how many subjects, but these are essentially the brains of healthy subjects, normal subjects, and we have, I believe you are familiar with these images. Are you all familiar with these images, these color maps? All familiar, yeah. No, I know that the people are familiar with it. But anyway, so this is essentially an anisotropy map where the color tell us where the fibers are oriented. So red is left-right, anterior, posterior is green, and through the plane, superior, inferior is blue, okay? And this one is actually an image of the mean diffusivity, so of the old trace of the diffusion tensor. As you can see, this is very different between CSF and the parenchyma, okay? And this is the type of anatomical variability we could expect in native space in our subject. So if we use the fractional anisotropy, so essentially if we use an anisotropy metric to perform the registration, which is actually what the most popular software for analysis of diffusion data does, FSL, you use, essentially you do a registration using FA, you see that actually, yeah, you get rid of a lot of variability in morphology, across these brains. But I would like actually from you, can you tell me something that perhaps is not working very well? Okay, clearly, we see that compared to the previous movie, here the internal capsule seems registered very well and so on. But what is not really optimal, I would say, or still problematic? The ventricles, right, yes, exactly. So the ventricles, you look at how they are dancing around. So the ventricles are not really nicely co-registered, and this is not surprising because look at the difference in anisotropy between the ventricle and the caudate. So the poor registration software doesn't know what to do. It doesn't find an information in the anisotropy map that will tell what to do, right? And so essentially does do a poor job in the ventricles. And then there is another thing that is really not that good. Color change, exactly. Yeah, the color changes. So look how it's dancing around. I mean, this should be registered. So again, if you bring these brains into registration, we said before, right? Different colors means different orientation of the structure. How is it possible that this portion of the corpus callosum that is oriented in the same direction now has the underlying tensor showing this crazy orientation that are dancing around? That is another very pervasive problem. Why is that happening? Because again, the FA will be a sort of a black and white image of this map. And so in a black and white image, the FA here is high as it is here high. So again, the software has no information in registering correctly these regions, okay? So now we go to what the TITK does. So essentially this software that is based on the tensor deviatoric, okay? And then you can probably see that now the things in terms of colors dancing around here in the corpus callosum or even here in this region, the situation is much improved because the tensor deviatoric contains also the information, the directional information of the diffusion tensor. But still we have very poor performance at the tissue gray matter interfaces, like here the ventricle, okay? And then, so Dr. Thomas uses all the information, so it has a good performance in terms of not having the colors dancing around, and a relatively good performance also in registering the CSF regions. Obviously, again, it's a compromise. It needs to decide, which feature of the tensor will be most valuable in different regions. But again, and this is essentially the final results of taking these subjects in the native space and doing a morphological warping into a common space. Okay, now let's go through some applications, and we can go quickly. So this is the only fully published paper that we have, and Neda Sadeghi is the first author of this. And this was an application to hereditary spastic paraplegia. And now I put in yellow the sort of important points of each of the example that I'm showing. So if you then get distracted, it's not a big deal. But essentially, these are the important points. So one point that I would like to demonstrate with this particular application is that diffusion tensor-based morphometry localizes disease to specific white matter pathways, and that the DTBM results are consistent with selective involvement of long-range white matter pathways. So this was important in this particular disorder, because this hereditary spastic paraplegia, in particular this genetic subform SPG11, is a form where, typical conventional MRI show a very thin corpus callosum, show atrophy of white matter, but there is a specific hypothesis that the underlying cause of the disease is a defect in a protein related to axonal transport. So the bottom line is that it manifests itself mostly as a motor disease, because the motor neurons are the ones that have the longest connection, right, from the cortex down to the spinal cord. So in this venue, you can hypothesize that probably white matter is not affected the same way, but that longer fibers are more affected than shorter fibers. And here you can look at the determinant of the Jacobian map. I remember that where you see dark, it means that patients had smaller structure than control. And you can see the morphometry done with conventional T1 weighted images. You see this diffuse reduction in white matter because T1 weighted images do not have contrast in this centrum semiovale, right? But if you look at the tensor-based morphometry, you can see that some regions are more affected than others. And you can see it throughout the brain, right? And even if you go down to the brainstem, is beautiful because you can see here that of the tiny brainstem, the actual fibers that are affected are the motor fibers. This is the location of the motor fibers. T1 weighted tensor-based morphometry just show some, hypoplasia or atrophy of the brainstem, but it doesn't really localize it to a specific pathways. And if you see which are the tracts that correspond to the affected regions, these are actually long-range tracts. So this is a tractography done by seeding in the regions where the volume reduction was most severe. And you extract beautifully, these most important long-range fibers, okay? Second example, application to normal brain development. Here, the message I would like to show and prove is that DTBM changes generally correlated with FA changes, but the regression slope changes in different pathways. So essentially, you can ask in brain development, as you probably know, during postnatal brain development, the anisotropy of tissue, or white matter, changes dramatically. So anisotropy is somewhat related to things that accompany maturation of white matter. With tensor-based morphometry, we are looking at the size of the structure. With the FA, we are looking more at the structure of the region. So this is actually a database, a publicly available database of pediatric data. And here actually are some, Dr. Thomas created brain atlases at different ages that one can use for registration of pediatric data. Look how interesting is the evolution of white matter structures in these. This is babies from 0 to 3 months. And this is conventional MRI. As you probably know, in conventional MRI, the contrast between gray matter and white matter changes throughout the first initial stages of postnatal development to the point in which sometimes you don't even differentiate gray matter and white matter in conventional MRI. And you can see that on tensor-based data, actually, you can see all this arborization of the white matter tree that becomes richer and richer. And then you can look at the time course of changes in fractional anisotropy, or you can look at the time course of changes in the determinant of the Jacobian, and then you can look at the correlation between the two. And there is actually a pretty good correlation in the log domain between the changes in the determinant of the Jacobian and FA, but the slope of this is different. So essentially, both are indices of maturation of structures, but in some cases, you may have structures that mature very early or remain very small, and then they change a lot fractional anisotropy quickly, or structures that actually change fractional anisotropy quite slowly and then and grow much more quicker. Okay. Another example, and I have just a couple of examples, and then we could conclude. So this is an application to Down syndrome. This was presented at the SMRM. The paper is the full paper is under review, and so the take-home message is that we have dramatic patients versus control DTBM differences with no fractional anisotropy differences. So before, in brain development, we saw something where fractional anisotropy was changing, the size of the structure was changing, and they were somewhat correlated. Here we have an example in which FA doesn't really show almost no difference, but you have mostly morphological difference. And then the DTBM allows the identification of selective hyperplasia of frontopontine cerebellar connection. So you can actually map which are the systems that are mostly affected. These are the demographic characteristics of the Down syndrome cohort and the control cohort. These some information of how things were computed. I don't need to go through each one of them, but again, just for the record, this shows essentially the pipeline for measuring things. We very often, a metric that we like a lot is this effect size metric, which is essentially a very simple metric. The mean of the patient minus the mean of the control divided by the standard deviation of the population. We like it because we find that statistics for imaging is a little bit of a difficult beast because you have to deal with multiple comparison correction with the known well-behaved data and so on. So sometimes you have the risk of being too conservative or too relaxed in your strict statistical assumption. These effect size maps gives you some feeling of really different, looks at the magnitude of the difference and then divided by essentially an index of variability, okay? And these are pretty informative. So these are effect size maps of the Down syndrome patients versus controls for fractional anisotropy, mean diffusivity, the T1 base a determinant of the Jacobian, so essentially morphometry done with T1 and morphometry done with the diffusion tensor. Now, look, if you look at these two images, they have a lot in common. This is good. I mean, morphometry is, morphological differences should be there in the T1 weighted images and in the diffusion weighted images. And in fact, in this gray matter region, both techniques reveal quite severe hypoplasia in the Down syndrome population. But if you go down more the brainstem and other structure, you can start seeing quite striking differences between the two techniques. And again, the ability of diffusion tensor-based morphometry to measure the size of individual pathways is interesting. And I wanted to point out this example of, for instance, at the level of the cerebral peduncle. You can look at this determinant of the Jacobian map. So again, where it's dark, it means maximum loss of volume in the patients. So at the level of the cerebral peduncle, we see some subdomains. So a medial one here, an intermediate one here, and a lateral one here, and they have different behavior, okay? So this is normal. This one is severely hypoplasic, and this lateral one is hypoplasic. If we do tractography from these seeds, we go to very different directions in the brain. And in particular, this medial part is a very well-known pathways that connect the frontal lobe to the pons. Okay, so this is really a selective involvement of fronto-pontine connection and then down in the cerebellum. Now, if you do the classical, and this is what is striking. So again, it's an invitation and looking at our data in a broader way than we usually do. Everybody does in analysis using this TBSS metric on FA, so the skeletonization, extraction of voxel-wise differences in FA. If we do that in this patient population, we find absolutely nothing significant at TBSS of FA. So essentially in Down syndrome, it seems that the structure of white matter is not particularly abnormal, but is the volume of white matter pathways to be horrendously abnormal, okay? And in fact, the DTBM reveal, even in the skeletonized version a lot of differences. Okay, then you can really look at various regions and so on. This is more related to the investigation of the disease, but essentially you can both in gray matter and white matter look at the degree of hypoplasia and work with your hypothesis to explain that. And essentially you go from regions that in a white matter, like the inferior cerebellar peduncle, transverse pontine fibers and so on, that are severely hypoplasic, to the splenium of the corpus callosum that is really not affected, is normal. Okay, I think this is the last example to this Möbius syndrome. And I must admit that although I studied as a neurologist, I really almost didn't know what this syndrome was. It's kind of a rare disease, and is a disease that involves the 6 cranial nerve and the 7 cranial nerve. The 6 cranial nerve is the is the abducens nerve, so it's used for abduction of the eye, looking laterally, and the 7 is a facial nerve, which is related to the mobility of the facial muscles. Okay, so these patients have deficit primarily of the 6 and 7 nerve. The important finding in this study is that DTBM identify atrophy of the medial longitudinal fasciculus as a hallmark feature of Möbius syndrome, and then DTBM results allow 100% classification accuracy in differentiating Möbius patients from control and congenital facial palsy patients. So the congenital facial palsy patients have the 7 cranial nerve deficit, right? So essentially they have a portion of the syndrome of the Möbius subject, but they do not have the ocular involvement. And the medial longitudinal fasciculus is actually a fasciculus that is involved in a connection between the nucleus of the 6 and the nucleus of the third cranial nerve. The third cranial nerve is the other most important oculomotor nerve that we have. And so coordinating that fasciculus is important because these two nuclei need to talk to each other and coordinate. If you want to move your eye laterally, you want the medial rectum to relax and not contract, okay? So the hallmark, the very interesting thing, and these are effect size maps that you can see, is that you have this region in particular where the medial longitudinal fasciculus is positioned that is very highly informative, okay? And if you take a narrow eye in that region and you look at controls, this is the value of the Jacobian. If you take Möbius subjects, these are the values in blue, are the values of the Möbius subject. So you have essentially an almost perfect separation between patient and control. And then if you look at the subject with cranial facial palsy that do not have the ocular involvement, they classify as the controls. So that region is not involved. So this is just to tell us that this was a very tough study to do, a study where obviously the quality of the images was extremely important. And again, we use all sort of tricks in the acquisition to achieve a perfect correction and co-registration of the data. But in any way, this shows if we are able to improve these things in the clinical arena, where we can go. Okay, so in conclusion, I think that diffusion tensor-based morphometry is a promising tool to complement conventional analysis of diffusion MRI for neurological application. It has great potential for personalized medicine, but it requires good data, not necessarily big data. So that, we see a big push, even from NIH, and I mean, I shouldn't say that on record, but in funding very large studies, I think we really need to focus on funding very high-quality studies, okay? And then we will have them there. And as a practical consideration, and here for the people, here at the NIH, that acquire diffusion data, I think that prospective diffusion MRI studies should be designed with blip up, blip down acquisition, including also all the diffusion-weighted images. This is an aspect that I didn't touch upon in the correction of the morphological distortion of echoplanar images, but what is typically done is that blip up, blip down is done only on the so-called B0 images, not on the diffusion-weighted images. It doesn't work very well. And it's also easy to understand why it doesn't work very well, because if the B0 images are homogeneous in a certain area, like the brainstem, the algorithm doesn't know, it corrects very well the contour of the structure, but it doesn't correct inside the structure. So at the end, the pathways get all warped up, okay? And we can have example to that, for instance, with the connectome data, if we work just with the correction used in the B0. So it's important to take home message, if you want to do a prospective study in diffusion, acquire both blip up, blip down, also for the DWIs. We are a little bit maniacal, we acquire also two different phase encoding directions. But, the most important thing is to have at least blip up, blip down in the DWI. And I wanted to thank people that have been key in these studies. As you have seen, a lot of papers with the Okan name as first author is really sort of single-handedly has developed most of the tools that we use for this analysis. Neda has been involved in many of the clinical applications and in analysis of in particular, she has been working for almost years on the Möbius project, and finally that paper now is under review. And Amrita also has been helping us in our group with all the analysis of this clinical data. Nancy at Drexel, she was at the NIH before, is involved with the Down syndrome study, and Irene Manoli has been sort of the clinical PI of the Möbius study. Thank you.
Okay, so I was curious, you touched upon it with the Mobius data at the end, but I was wanting to know for the personalized medicine, if you could expound upon that a little bit more. So for, healthy subjects, when you look at various areas of gray matter, in addition to the white matter, do you find that they cluster with similar volumes, or not? I mean, this was in particular, you showed the medial
Medial
lemniscus.
longitudinal fasciculus.
Oh, okay, yes. But so I was wondering about other areas of the brain. How much are they, do you think, consistent between the healthy control population?
I think it's really an open field. It's actually a beautiful project that we would like to do on the human connectome data, looking at these aspects. Is exactly what. So what is the variability, and how does that variability in morphology relates to cognitive features, to other aspects again, and I don't think we know yet, and we really need to work on good quality data and be able to look at these things, and I think this is a tool that can be used for that purpose. Unfortunately, one thing that has to be said is that the cortical regions are sort of difficult to study, again, because we need to respect diffeomorphism. So if we have 3 gyri in one subject and 2 gyri in the other subject, there is no way of having a diffeomorphic registration that is valid, okay? So the one-to-one correspondence become violated. So typically, you achieve a very nice registration of central structures. At the level of the cortex is a little bit more difficult. But you can actually try to see if there are maybe, the things that may group people because of similarity in this more peripheral morphology, and then essentially use that as the grouping type of criterion.
With your Mobius data, it looked like, I think you were plotting the Jacobian on the y-axis. So were they less variable than healthy controls?
I think the variability was similar. The thing was normalized. Okay, the data I think is here. So you say here, now I have a difficulty seeing the colors here. So this is the variabilities from 0.5 down to 0.25, right?
Yeah, I guess I don't mean variability. I mean the extent of the distortion for the patient seems less than.
No, this is after the correction of the distortion in the PI. This is the morphometry. So both patients and controlled had the correction of the echoplanar images. That is to go to the first step, having morphologically faithful diffusion data. This is a step that you don't need with T1 weighted images, because T1 weighted images are not distorted, okay? So that is the first step. So that was applied to patients and controls. The data that is shown here is that you take a template for the population, and then you register each subject to that template. And so then the question becomes, how bigger or smaller is the structure locally at each location with respect to the reference? Okay, so let's say you have a population of controls, and then you could register other controls to that population of controls, and then you register your patients to the population of controls, and then you plot the data. So you see that if 1 is the mean value for the control reference, your controls are essentially around this 1, right? With a certain variability. I mean, we have inter-individual variability in size of the medial longitudinal fasciculus or that particular region. But then, again, the patients are very clearly separated with a much smaller structure. So that is but this is a step that comes, so it's not really related to, how abnormal is the morphology, right? One is the artifact, essentially, the distortion in the echoplanar images. The other thing, once you have corrected for that distortion, you bring into a common template and you do your registration. Okay?
I had a question. Do you get an uncertainty measure with the Jacobian? So when you warp someone to something, because we're often used to having a statistical quantity. If you do a GLM, you get a beta value, and then you have a statistic associated with it that can also tell you the variance of it, because you estimate something plus or minus a bit. With the Jacobian, do you get that?
But not really, because you get a certain deformation, and then you have a value of the Jacobian that is associated to that deformation. But this is not dissimilar than what you have with FA, right? You compute your FA. So yeah, sure. If you do a tensor fitting, you could actually do error propagation and put an estimate variance to your FA, but indeed what you actually generally feed your statistical program with is the estimated value, which is your best guess, right? So
you could include there are statistical programs where you can include the uncertainty as well.
Yeah, I think again, yeah. I'm not the expert of the registration. This is a good question for Okan. I believe that you probably can look at again, the registration is an iterative process, so you converge to an optimal solution. You can probably express some sort of uncertainty based on how you converge to that solution. But
second question, this is the average Jacobian of a selected ROI. Where are these ROIs coming from? Because your Jacobian is a voxel-wise measure. What does it mean in ROI
right.
here?
You're right. You will be an excellent reviewer because you would chase me. No, yeah. These are actually the details of the study is this one, that we started with a voxel-wise analysis in a subgroup of Möbius subjects that have the pure pathology, okay? So there are complicated Möbius and there are pure Möbius. So the group so we had the controls group and then a group of a subgroup of Möbius. That voxel-wise analysis, as I had identified in essentially the effect size map, that region as particularly relevant. So then we took that region and we took another set of subjects, and then we did essentially the validation on the accuracy, okay? So that region was identified on a population-based thing. Then we selected that region as a candidate region in terms of discrimination between patients and controls, and then we took a new set of patients and ran an analysis on that region.
So you do have a measure of variance if you're doing this across the ROI, because you start with a voxel-wise number. You do get the variance through the ROI.
You can get the variance through the ROI. One thing also to be that is important is that the Jacobians are typically smoothed out a little bit, and these are all technical aspects that are open for discussion because, for instance, even within our own group, I mean, Okan is always skeptical because you can actually break the tissue, right? So if you smooth out too much, you are essentially averaging across structures that are not similar to each other. If you, don't smooth, then you can break the field, and then you start having negative Jacobians, which is clearly pathological. So, but it's true. I must say that the statistical properties of the Jacobians are somewhat a little bit smoother already than the other voxel-wise matrix.
Because it's generated from a smooth field.
Because it's generated from a smooth field, yeah. Exactly. Yeah.
The other point, the common template that you generate that's just from the control group.
You can do again. If you have a large number of subjects, you can do everything you want. If you have a limited number of subjects, then these are all very valid questions. So we typically actually do. If we have a balanced number of controls and patients and the anatomical differences are not huge, it's wise to actually do a population template. and use that as your, if you need to essentially analyze these differences based on a group of subjects that you would include in the analysis, then you risk to be biased if you just choose a template built from the controls. So we tend to do a population templates, and then we do the statistics, each subject goes into the population template, and then that will be a sort of a common ground between patients and controls. And then you can do the statistic between the determinants of the Jacobians of the individual subject that belong to each subclass. So that actually is what I probably is the best thing to do if you build the template with your own data. If you have
two groups, with the combination of both.
With the combination, building a population template. We tend to actually always recommend to build a population template rather of data acquired with with the same image modality, rather than going into, for instance, an enigma template or a very smooth template. We have noticed a lot of mistakes. If you use the wrong template, which is not consistent with the data you have, you really lose a lot, and you have a lot of uncertainty in the registration. But if you would have, for instance, a set of normative data collected in a certain normative population with the same scanner and so on, I think the Department of Radiology could build normative data and then have their own, each patient challenge, against this normative database. I think it could be possible.
So here, where you have your Jacobians all around one for the controls, this is with the control template, right? So
Yes.
if you bet a common one.
If you would have had a common one, yes, because this is true. But this one is where we actually, actually, I do not remember if the controls then for the classification was another group of controls. For the Down syndrome, for instance, we did exactly that. So it's around one for the controls, but we have a completely separate population of controls. So we have, let's say, because in that case, actually, we had more controls than patients, and so we could build a control template from unrelated subjects that were gender and age matched, and then essentially use that as a target for both patients and controls. And that actually, I think, is very nice. If you have essentially the luxury of just using a bunch of subjects only to build your template, is an independent population essentially, rather than building from your own, from the subject that you are analyzing. Okay, thank you.